generators and relations. Doesn't generate. Take a pen. Okay, as before, we have our regular polygon M. We have its symmetry group. We fix a flag. Do you remember what is a flag?
Yes.
Okay, so we define centers of our faces of this flag. So for the zero-dimensional F0, it coincides with itself, yes. And now we take the center of the segment, the center of the square, and the center of the whole cube. So H1 is spanned by these points. We have n planes, which will be our mirrors of our reflections.
I'm just confused. H1 is generated by
We
C1?
forget I minus 1. All but C I minus 1.
Okay.
So by this construction, all the hyperplanes contain Cn. You see? We never forget it. Cn is the center of our polygon. I can show what will be these planes for the cube. H1, it will contain C1, C2, and the center of the cube. So, let me draw 3 cubes, and then draw all the hyperplanes. So, clearly, since H1 contains this point and this point, it contains all this stuff. And it contains the center, so it contains the center symmetrical one. So this will be H1. Okay. Now what about H2? C0, C2. It means that this and this, so the diagonal, so the opposite diagonal. So this rectangular section. And now what about H3? H3 is 0 to 1. So this stuff, clearly this one, and this one.
Again something rectangular.
Sorry?
It will be again something rectangular.
Yes. Yes. So these are our generators, and our aim is to give the relations and to study all such groups.
Do this group have some name? This H1, H2, H3? They have some
These are
name?
hyperplanes. They will be simple reflections. They will correspond to, in some sense, simple roots.
Simple roots.
Yes. It will appear soon. Our lecture course is called the root systems.
Yes.
It is very close to root systems. It is already very, very close. We will see it at the end of the lecture. So, what I've told. So, I said that if I start my process with some phase Fm of our polygon, if I construct hyperplanes Hi prime for this phase, if I follow this instruction but live in some n-dimensional subspace, then if I add back the centers Cm plus 1, etc., Cn, it will be exactly our hyperplanes HI. So this construction remains valid when I look at some face of my polygon.
Почему только шатим, а не ладно.
Потому что мы формировали, так как нам хочется красиво. Okay. We can also study what is the symmetry along the last one. What is the symmetry along HN? So I state that it is the one generated from the last lecture. So symmetry along HN. What can we say? We say that HN contains the face Fn minus 2. N minus 2. Why? So Hn contains C0. Hn contains C0. Then it contains C1, etc. It contains Cn minus 1. So if it contains C0 and C1, it will contain the whole F1. If it contains the whole F1 and then C2, then it contains F2, and so on. No, if it contains up to Cn minus 2, so it contains Fn minus 2. And now, what else? I know that the hyperplane Hn, and then the segment Cn minus 2, Cn minus 1, they are orthogonal. Why? Because Hn, what is Hn here, and C, no, one moment. I want to say that the reflection along Hn, it is a symmetry which, so what is sigma Hn? I want to say that it is exactly what we've had in the previous lecture. I mean, this is one of the symmetries which preserves Fn minus 2. Okay, there is no need to prove anything because we know we know that it preserves our polygon and that it maps two faces of dimension n minus 1, one to the other. There are two different faces which are mapped one into the other via a sigma Hn. What is orthogonal? So there are there is Cn minus 1, Cn minus 2, Cn minus 1, which is orthogonal to Cn minus 1, Cn. But this is not what I want. So one moment. I want to say exactly what is mapped to the other one. Okay, so H yeah, exactly. So C N no, that doesn't work. Okay, so we have more or less discussed the symmetry Hn. We said that it can be used in this theorem as this one. Okay? This can be sigma Hn.
Теорема с прошлого раза или то, что мы сегодня хотим доказать?
Это теорема с прошлого раза. В прошлый раз мы доказали, что сим m порождается сим какой-то грани и одним отражением, которое переводит грань. Вот эту вот fn-1 соседнюю. Ну, собственно, вот это вот мы показывали, что у нас есть отражение относительно всех граней размерности n-2, и, соответственно, вот это вот тоже будет. Поэтому оно подойдет. Хорошо. So, the statement, which is very similar to the theorem from the previous lecture, theorem is that sigma h1, etc., sigma hn generate the sigma m. How can we prove this statement? We can use the induction, and we almost repeat the proof from the previous lecture. So induction by M. For example, for n equals 1, this is obvious. This is obvious because we have only h1. This is our h1. Clearly, it generates sim m.
Но мы сейчас 7m будем воспринимать как вот группу, порожденную симметриями fn-1 и сигма.
Да. По сути, мы просто пройдемся по доказательству из прошлого раза и скажем, что как бы хватит ровно этих кашек. So what is the induction step? Step as before, we know that sim m is generated by sim fn-1 and sigma hn. Okay?
Нужно еще раз. H это плоскость перпендикулярная fn-1.
HN. Да. Да. Но мы ее строили немножко через точки мы проводили. So HN contains it contains C0, C1, etc. up to Cn-2, which is equivalent to Fn-2, at the center of our polygon M.
То есть То, как мы в прошлый раз строили, это то же самое, как мы сейчас построим.
Да. No, just, is it clear that any hyperplane, any hyperplane which contains this, contains fn minus 2? This can be done by induction. If a plane contains one end of the segment and its center, then it contains the whole segment. Then if it contains this segment and the center of the triangle, it will contain all the triangle. If it contains the whole triangle and the center of the tetrahedron, it will contain the whole tetrahedron. And so on. So Hn contains Fn minus 2, and it always contains the center of M. So yes, this is exactly the reflection which we've had at the previous lecture. Now we can use the induction and say that the sim Fn minus 1 is generated by sigma h1, etc., sigma hn minus 1. I've said at the beginning, that we can add some dimensions. So if we construct hyperplanes inside Fm, and if we compare it with the construction of the first one, the first M hyperplanes here, then exactly we should add Cm minus 1, etc. Cn. So this is correct. Okay, we can look here. This symmetry is in fact the symmetry of the square along this line. We just add one dimension on which we act trivially. And this one, H2, is in fact the symmetry of this square, which is extended to the third dimension trivially. So this is correct to say that sim Fn minus 1 is generated by these reflections. And now the whole sim M is generated by the prescribed N reflections. Any questions? Давайте задавать вопросы. Только профит честно. Если есть какой-то конкретный вопрос, вы задайте. Okay. Now let us define the Schlefe symbol. I've decided to define it not as in the book, but as in Wikipedia. It will be more convenient for the proof. So, as it was at the previous seminar, what is the Schlefe symbol? So if we have a regular polygon in dimension n, so if this is n, then it will be a sequence of integers p1, etc., pn minus 1. So let us define it inductively. For a regular polygon on the plane, P1, the only value it is the number of sides, which is the number of vertices. Okay?
Number of чего? Sides.
Да. Сторон и вершин. Ну, если это n угольник, то скажем, что это n. Чисел. So for pentagon, Q1 equals 5. We have 5 sides and we have 5 vertices. So in dimension 2, the Schläfli symbol is the only value, one integer. And it is equal to the number of sides and the number of vertices. Now suppose that...
А мы вот эту теорему типа уже доказали?
Какую теорему? Теорему вот это вот, да, доказали. Я же говорю, задать вопросы.
Вопрос, как мы доказали, ну ладно. Можно? Ладно. Давайте сначала символ.
Давайте. So if dm equals 2, then Q1 is this. Now, if dm is greater than 2, what is our construction? So take P1 is the number of sides of F2. So it equals the number of sides of any two-dimensional face. Since our action on flags is transitive, each two-dimensional face has the same number of sides.
Это то, что мы любой флаг можем
Да.
привести, да? То есть,
Да.
типа, что они одинаковые, все эти
Да.
двумерные.
У нас не бывает футбольных мячей, в которых какие-то там восьмиугольники, какие-то четырехугольники, потому что флаг это как бы вот флаг содержит двумерную грань, поэтому такого не будет. Okay, so we said that P1 is the number of sides of any two-dimensional face. Now, in some sense, some star construction. So suppose this is F0 and Q1, etc. Qk. And all the vertices which are joined by an edge with F0. So I will explain right now why Q1, etc. Qk is a regular polygon of dimension n minus 1.
QI is сосед.
Neighbor.
Сейчас
Да. All the vertices adjacent to F0. So I can draw for the cube of dimension n minus 1. What is this construction for a cube? F0 was here. So we will have Q1, Q2, and Q3. So how do we construct the Schläfli symbol for a cube? P1 equals 4, because any two-dimensional face has 4 vertices and 4 sides. And now we construct Q1, Q2, Q3. It is a triangle. And then we take the Schläfli symbol of this polygon and we write it instead of P2, etc. Pn minus 1. So P2 now equals 3. So P2, etc. up to P n minus One, it is the schlechteste symbol for your one, etc. QK. Maybe I should prove something.
Ну, знаешь, что он правильно?
Я могу объяснить, если не поняла, что за это. So, what is correct? We know that sim M acts transitively on the flags. So, we can construct many flags starting with F0 and F0 QI. Okay? So, these flags will be, we can map one into the other. So Y, Q, 1, Q, K is regular. We can F0, Q, I can be mapped to F0, Q, J by sim M. Okay? So this will be a sequence of reflections. We can take only the reflections that preserve F0, and they all preserve the center of M. So we can take a hyperplane which will be orthogonal to F0Cn and passing through a Q1, for example. Okay? So in one direction. Any flags can be mapped one into the other. So it will be a reflection which preserves the line F0Cn. So all the other Qj will belong to this hyperplane. Q1 belongs to this hyperplane, and it is preserved under the reflection. So all the other Qi belong to this hyperplane. Okay?
Вот на примере куба.
Да.
Мы берем диагональку.
Да. Проводим через Q1 плоскость ортогональной этой диагонали, большой диагонали.
Да.
Говорим, что если, ну вот мы провели через Q1, но поскольку симметрии, которые переводят флаг в флаг, они на самом деле сохраняют диагональ, значит, это по сути симметрия треугольника вот этого вот. На диагонали действует тождественно, а на этом треугольнике мы по факту и действуем.
То есть, например, если мы хотим переставить Q1 и Q2 местами, это мы вот флаг такой,
Ну,
вниз.
вот этот вот, да, этот флаг, вот этот
А
флаг.
если поворот, например, хотим?
Какой поворот? В смысле, вам надо флаги переставить. Чтобы переставить флаги, у вас есть хотя бы одно преобразование.
Ну, если я хочу попробовать эти переставить местами, это же прям симметрия.
Нет, ну как бы у нас есть симметрия треугольника, поворот, и в кубе есть поворот на 120.
А, значит, флаги надо переставить.
Но нам надо уметь представлять флаги,
А
да.
на треугольнике флаг это только точка из стороны.
Да. Ну, по факту треугольник тоже как бы включается, но он везде всегда включается, это не содержательно.
То есть поворот.
Да. Any questions?
А как вот задается на кубе флаг, вот на треугольнике, допустим, ну вот возьму вот точку в сторону и ну, поворот на 120.
Нет, флаг это цепочка граней.
Да.
У нас
Вершина,
поворот.
ребро.
Еще раз, во-первых, у нас сейчас все флаги содержат F0. Мы не начинаем флаги с других вершин куба.
Сейчас вот как доказать, что он правильный? Доказать, что ли? А?
что это треугольник, правильно?
Да, доказать,
А, ну-
что любой флаг можно перевести в любой флаг движением.
Сейчас скажу, любой флаг вот в этом,
Да.
в этом мы достраиваем. То есть,
Вот я хочу рассмотреть флаг, там Q1, ну и
Пожалуйста.
какая-нибудь сторона из Q1.
смотрите, берем F0 в качестве первого элемента.
Так,
Сейчас хороший вопрос, давайте вот так вот сделаем. So, if we take any flag here, it corresponds to a flag in the initial polygon. First we take F0, then we take the span of F0 and the zero-dimensional element here. This will be this by construction. This because it is span of 0 at Q1, and the span of this segment and of 0, this will be this face. Okay?
так. И, допустим, я хочу перевести флаг Q2, вершина, и который в Q3. Ну, с поворотом 120 градусов.
Я поняла, сейчас нарисуем, сейчас сделаем все. Okay, if you want to send into this flag, you just say, there is another flag here. Oh, this one. And Q2, Q3.
Нижний. вот этот.
Mhm. So there is so we have two flags on the cube. There is an element which sends one into the other one. Yes, indeed, it is a rotation along this line by 2 pi over 3. And it corresponds exactly to the rotation here.
Ну, на примере понятно, только вот не так. Вот, почему? Может, ну, то есть Q1, Q2 перешло в Q2, Q3, да?
Подожди, что сейчас? Вообще тут конструкция, ей как бы без разницы. Пример у вас или не пример? So this construction, it survives in any case. If we take some face here and we add F0, we obtain a face in the initial polygon. Do you believe or not yet?
Я believe, но я не до конца понимаю, почему это работает, но ладно.
Ну, подождите, давайте мы еще что скажем. Мы скажем, что многогранник задается неравенствами. Поэтому so a polygon is given by some inequalities, so a face is a subset where some inequalities vanish. And we add one more dimension, we add that it vanishes also at F0. So we cannot take, for example, the altitude of this triangle because it is not a face. We take only something external. And external for this triangle is exactly external for the initial polygon. Okay? So we said now that Q1, etc., QK is also regular. So by induction, we have its Schläfli symbol, and we can write it down for our polygon.
Правда, тоже такой вопрос, а почему они лежат в пространстве размерности на меньше, все эти вершины?
Я сказала. Давайте еще раз скажу. Сейчас я тебя просто скажу. Что я сказала? У нас есть Q1. Через Q1 мы проведем гиперплоскость перпендикулярно вот этой главной диагонали. В нем лежит Q1. Дальше все флаги, которые начинаются с вот этих вот, F0 куитые, F0 кужитые, переводятся в какой-то композиции отражений. То есть мы можем без ограничения общности считать, что мы вообще брали только те отражения, которые F0 сохраняют. Они сохраняют F0, они сохраняют центр, значит, прямую гиперплоскость ортогональную F0 центр, они все их сохраняют. Да, и все остальные пушки тоже покупают. Okay, any questions? So I have defined the Schläfli symbol.
Это так, как в семинаре передается.
Да. So finally I decided that you will prove yourself in the seminar that the Schläfli symbol equals the following object. So in fact PK equals the number of k-dimensional faces between fk plus 1 and fk minus 2. We assume f minus 1 is assumed to be the empty set.
Еще раз. Pk is the number of
Faces of dimension k between fk plus 1 and fk minus 2. I can explain it for the cube.
Between fk plus 1.
So for the cube, what is it for the cube? What is P2? P2 is the number of faces between F3. So which are faces of F3 which contain K minus 2, F0. Number of faces of dimension 2 which contain a vertex. There are 3 such.
F3 это весь.
Да, весь куб. And P1 is in fact the number of 0-dimensional faces of F2 of a square with no conditions because we assume F minus 1 equals the empty set. Okay? F2.
Ничего не понимаю. Еще раз, количество граней, вот P2, количество граней размерности 2 между F3 и F0.
Да, которые содержатся в F3 и содержат F0.
То есть внутри куба, который
Да.
содержит одну вершинку.
Одну заданную вершинку, да.
Примерных, то есть
Квадратиков.
раз, два, три.
Да, их 3.
Примерных, то есть сторон, содержащих какую-то грань.
Нету. So no conditions when we seek for P1 because we assume that F minus 1 is the empty set.
4.
Да. Magic. 4 and 3. Two definitions give us the same. I don't know which definition is nicer. But I decided that for our proof, the first one is more convenient. You will prove that they're equivalent. If nobody proves it, it will go to this sheet. This is very important. I think you should think of it yourself. So we have two definitions. And you will have to check that they're the same. Okay. And now I want to state our main theorem for today. Did you copy the definition?
Yes.
Okay. I said that we will have generators and relations. Our theorem is that M is generated by sigma H1, etc., sigma Hn with the following relations. First of all, clearly, since they are related, they're symmetries, they equals the identity. Then sigma Hi, sigma Hj commute when they're not adjacent for I minus j at least 2.
Hj, Hi.
Yes. Я не умею красиво писать этими маркерами. Hi. And the last one is that sigma Hi, sigma Hj power no. Sigma H I plus 1 power Pi equals the identity. Maybe I should state the example.
Should we say that sigma hi is not equal identity? That it's not identity involution?
It is, I mean, geometrically, these maps are not identity. They are symmetries. They cannot be identities. If we speak about generators and relations, it is assumed that the generators itself, they are not identity. Example, do you remember the dihedral group? Do you remember it?
Sim M.
Спасибо. What is the dihedral group? What are H0 and what are H1 and H2? H1 is this one. This is H1 and this is H2. Sorry, H1. This is 1. So we say that the group DM is generated by two symmetries such that their product has order M. Sigma 1, sigma 2 power M equals the identity. Do you believe in the step?
Отчетности M не зависит.
Нет, не зависит.
Для куба это диагональная.
Сейчас, это квадрат. Если вы так хотите, я вам нарисую квадрат. Тут будет точно так же. This is H1 for M even, and this is H2. In both cases, this angle is 2 pi over, it is 2 pi over 2m, so pi over m. And its double is 2 pi over m, so has order m. Okay, this is the example to convince you that it is indeed true. Okay, let us check these relations. So, why is this true? If I is less than j, then we can find k such that I is less than k is less than j. So, in fact, we have two hyperplanes. If we prove that they are orthogonal, then we are done. If they are orthogonal, then the composition is the rotation by 2 phi. If phi is pi over 2, then they both are the rotations around the common space of dimension n minus 2. Понятно?
Если угол между ними фи, то...
Если угол 90 градусов, ну это у нас на самом деле гиперплоскость размерности n-1 в двумерном пространстве. Но если угол между ними будет 90, то они действительно коммутируют, потому что и то, и другое будет поворотом вокруг их общей штуки на 180 градусов. Там будет блок минус 1, минус 1. Хоть в одну сторону, хоть в другую.
Это мы сказали, что вот вторая, да?
Это первую часть я объясняю, но я еще не проверила, что они ортогональны.
То есть, если мы покажем, что если между ними собирается хотя бы 2 и эти перпендикулярны,
Okay, why are these hyperplanes orthogonal? What do we know? We know that C I minus 1, C K minus 1 is orthogonal to CK minus 1, CJ minus 1. Okay? Because, for example, we've had a triangle, and if we add another center of, so if this is a face of some polygon of greater dimension, then clearly the segment from this center, the new one, Cj minus 1, is orthogonal to the whole plane containing this face. So this is Ck minus 1, and this is Ci minus 1. So I state that what belongs to both hyperplanes. Ck minus 1 belongs to both Hi and Hj. And then, how should I draw this? This will be Hi, this will be Hj. So Ck minus 1 is here. Then Chj doesn't contain this one, but it contains Ci minus 1, and this contains Cj minus 1. So it means that two hyperplanes are orthogonal. And we are done with the first part of this theorem. And now the second. Why sigma hi, sigma hi plus 1 power pi is the identity? So I want to prove this by induction. Induction. So this I prove. This is induction by I. The easiest is sigma h1, sigma h2. What is sigma h1, sigma h2? The theorem states that it is of order p1. Let me go back. Where is our cube? Where is our cube? What is h1 and what is h2? H1 contains it contains C1, C2, etc. And this one contains C0, C2, etc. So in fact, all the life is inside F1. Inside F1, we have altitude and we have the line passing through the vertex. Exactly as in our dihedral group. So in fact, we know that it is the rotation in the place of the face F1, and it contains C2, etc., Cn. So just we extend it by identity to the remaining dimension. And the composition is indeed a rotation of order P1. Okay? вопросы?
Ну, в примере кубов понятно, конечно.
Да, в принципе, я сказала для любого многогранника.
Ну, типа, работает в одной грани. Да?
Да. So, this is in the span of F1, F2.
Откуда мы знаем, что между как бы H1 и H2 угол это 2π делить на 2.
Okay, I will draw it in general. What is F2? So this is F0, a vertex. This is F1. Okay? And now it is a regular two-gon. How do we construct it? So H1 does not contain F0, but it contains the center of this face. It contains the center of the P1 gon, so it is something like this. And by construction, F1 contains this one and this center. So the angle between them can be formed from this triangle. So yes, so its order equals P1. Now, what about
Мы говорим, что именно порядок такой, и все-таки мы просто в эту степень возведем, получим тождественность. То есть порядок в целом может быть делительным.
порядок?
Ну, то есть,
Мы назовем дворник.
нет, туда, а там вот все это надо. То есть формально написать, что порядок прям такой. Ну, то есть, мы когда говорим в степени.
Я напишу.
Ну, в смысле, и в целом, да, то есть
Да, конечно.
порядок PI. Ну,
Да.
здесь понятно, да, но...
Потому что это, как бы, это же сторона, которая содержит машину.
Нет, тут, в общем, на случай...
В общем виде, это верно.
В смысле, да, что мы это в теореме, как бы, формально мы говорим, что не просто в степени PH, а просто порядок.
А, ну да. It was the induction step. So in the induction we fix n, but we shift I. So we can no, the induction will be both by n and by I. Suppose that for all the smaller dimension it is true. Now let us prove for dimension n. Also for dimension n, I equals 1 is done by hand. And for the greater values of I, the trick is as before. So how do we prove the step? If I is at least 2, then H1 and HI and HI plus 1, they contain F0. Okay? And we say that, in fact, we can say that, in fact, HI and HI plus 1 act on Q1, etc., QK. We took a section of our polygon by some plane orthogonal to F0, Fn. So, in fact, HI and HI plus 1, they preserve F0, F0 Cn. Cn. So they act on this hyperplane, and the order equals the order here, and by induction step it equals pi. And we are done. I can show you how it works at the cube. So where is our cube? Oh, H2 and H3. In fact, they both can preserve this diagonal.
Cool.
Главное, вот эту главное. So they preserve this diagonal, and in fact they act in this triangle. H2 is this symmetry, and H3 is this is preserved, is this symmetry.
F0 is 0.
F0 is here. It is preserved. It is in the plane of reflection. Q1, Q2. If these are Q1, Q2, and Q3. Q1, Q2, and Q3. Here, Q2 should be preserved. So Q2 is preserved. Now, in this one, Q3 is preserved. Yeah. This is H2. And this is H3. So do many. Okay. So by induction we are done, and we have proved that sim M is generated by these n symmetries with the following relations. So in fact, we can. How can we relate it with the previous, with all the previous stuff? Suppose that each hi corresponds to a vertex of a graph. And suppose that we join I and j by p by by the order of order h I, sigma hi sigma hj minus 2 edges. So almost all pairs, this means that the order equals to 2, almost all I and j are not connected. But the adjacent ones are connected by p1 minus 2, etc. Pn minus 1 minus 2 edges. So we have such a graph.
Почему никакое сигма hi, сигма hj не имеет порядок 1, то есть ему тождественно.
Why it is not an identity map? Because we know that in some dimension it is a rotation, and we know what is the angle of the rotation. So if we take sigma hi and sigma hj, and we assume that j is greater than I. Suppose that we act, suppose that j equals m. Then we can perform this construction. We can perform it. We make this construction. We can make hi equal to h1. And we will see exactly that it is a rotation. It is not a trivial map.
And any pi is not equal 0 because we haven't trivial polygons.
Yes, yes. Any polygon has at least 3 sides. So in our symbol, all the values are at least 3.
So each neighbors I and I plus 1 is connected by
Yes.
at least one edge.
Yes, so for the cube we will have such a picture. And for the simplex, if we define the Schläfli symbol inductively, any two-dimensional face is a triangle. Then if we make such a star construction, we just obtain the smallest simplex. It will be 3, 3, 3, etc. 3, and so the graph will be just this one. We have met these graphs.
Каким системам корней соответствует?
Ну как BNCN, B33, и AN. So this is B3 equals C3, and this is AN. If a simplex is in dimension n, then it corresponds to AM. Okay.
Can you explain this number of edges, how you get it?
Sorry?
You were saying that if I and j are not adjacent, then we have certain number of edges between them. And if they are adjacent, then this p numbers come.
No. I say that this definition works in any case. I write order of sigma hi, sigma hj minus 2. So in this case, this order of this stuff equals 2. Okay? We just multiply once more by hi and then by hj. And we obtain that this order equals 2. So if I write this minus 2 edges, we will have no edges between the ones which are not adjacent.
And when they are adjacent, they have
When they are adjacent, the order is pi. Pi by our construction is at least 3. And we draw pi minus 2 edges. Pi minus 2. So for the cube, it will be P1, P2. It was equal 4, 3. So I write 2, 1. And for the simplex, its Schläfli symbol was 3, 3, etc. 3. So I subtract 2. I obtain 1, 1, 1, etc. 1. Okay. So, can I continue for maybe 15 more minutes? Okay. So what is a reflection group? I should define a reflection group. It is a finite group generated by reflections. So we can say that in fact it is generated by reflections H alpha, and we can construct the following set. The set of plus minus alpha. So clearly this set will be invariant under all the reflections. So phi is invariant under all H alpha. And the second is that if we take a line and intersect it with phi, it will be plus minus alpha. Okay? So if we have a finite group, we just can draw alphas for all the reflections, and it will be true. So phi will be finite. And it will be true that, in fact, no, I will prove it later. Okay, this is the definition of a reflection group. And what we have done, we showed that if M is a regular polygon, then its symmetry group is a reflection group.
Now we want to prove that all such graphs are Fourier graphs.
More or less. Yes. Okay. If you want, I can draw you the answer. Okay. So, but I will not prove it right now. We can obtain the following graphs. We know AN already. Then we know BN. So for a cube of dimension n, it is in fact possible. If you know what is the Schläfli symbol of a cube, then this is possible. Then we have F4. And now three more answers which we didn't meet before. It was this one, then this one, and this one, which corresponds to the dihedral group. Multiplicity is m minus 2. So these three graphs, they did not appear as the classical root systems which work for the Lie algebra. This is because in this set of axioms there is no 2 alpha beta divided by alpha is an integer. So we have omitted one axiom of root systems. And we will have to reprove from the very beginning that we can correctly define the simple rules, that all the bases are conjugate, and we'll have the same stuff as the fundamental domain of the corresponding group. This will be done, so, and the classification will contain more answers. Maybe I can just say, how can we define a phi for a polygon M? Okay?
Получается, для правильного там dn, g2 не получить.
Чего?
Вот вы нарисовали АН, БН это 4, а ДН, или сколько там, да, ДН, G2, их не,
Да, давайте я скажу.
их не бывает для правильного или как?
Не бывает, не бывает. Okay. What is the corollary?
Е6, Е7, Е8.
Не бывает. Сейчас. The corollary is that
Е6, Е7, Е8, там это
the graph which we obtain will be linear. So linear means that it can have multiplicities, but there are no such fragments. If we forget multiplicities, we will not have vertices of degree 3. Yeah. So no dn, no e6, e7, and e8. Okay. Just we will not need it today, but I want to present.
H2 вот там сидит, да? То есть как бы...
Да, H2 будет M4.
H2 не тройной? 5.
Нет.
G2 двойной?
Сейчас. Нет, тройной. Сейчас, подождите.
Не тройной, всего.
Сейчас соображу. Тройное. Ну, сейчас эти картинки нарисуем. Прямоугольник не так много. Да, он будет тройной. Но у нас как мы элементы писать. Он будет это 6. Okay, a good question. In our previous classification, we've had the G2. What did multiplicities mean in the previous setting? It has something to do with angles. So we said that the angle between alpha and beta was equal to pi over 6. Okay? Pi over 6. It will correspond to m equal to 6 here. So when we pass here, we get m equal to 6. So what does it mean if we have two reflections with the angle 2 pi over 2 pi over m? It means that the angle between the mirrors is pi over m. Okay, so we have m lines Let me draw 6 lines. So these are 6 lines which correspond to some root system. It means that I choose the alphas at these lines in order to satisfy the previous axioms which included to alpha beta alpha integer. So this is m equal to 6. This is possible to choose alpha and beta. This will be length 3 and this will be of length 1. And this will be again of length this one. Okay?
То есть в данном случае это не n-угольник.
Сейчас скажу. Здесь это m-угольник. А здесь у нас было другое соответствие. У нас было тройное ребро. Оно соответствовало... Мы же там по табличке выбирали краткость, помните?
То есть Ш2 оно соответствует шестиугольнику.
Ш2 следует шестиугольнику, да.
Но тем не менее сумма не 6 минус 2, 4, а 3.
Ну, это две разные задачи.
То есть вот там это...
Вот это немножко не разошлись, да.
Хорошо.
Спасибо за ваш вопрос, я тоже, да, сама не заметила. Но в целом, да, они разошлись. Еще раз. If m equals 5, then this does not correspond to classical root system. Because we cannot find alphas on our 5 lines in order to satisfy this stuff. So these are very close problems, but a little bit different and with different answers. Okay? I wanted to draw 5 for the next time, but maybe I will not do this. I just say that we will reconstruct all the stuff about root systems next time without this axiom. And I stop for today. Maybe I will add one more problem to the seminar. This will be for you to construct exactly phi for the polygon M. Can you write down phi exactly? Okay? Then that's all for today. Thank you for your attention.
And for which regular polygon is match? Короче, это 4.
Это четырехмерный.
А?
Он же четырехмерный.
И что там за основание? То есть это что-то непонятное, необычное?
It has, for F4, it has F4 2 power 7 times 3 power 2 elements in the symmetry group. We will construct it using quaternions. Okay?
То есть АН это симплекс,
Да,
БН это гиперкуб,
да,
F4 это какая-то штука,
да.
всякие икосаэдры, октаэдры, декаэдры, они вот сюда ушли.
Сейчас, подожди, кассетры до декаэдры. Да. Кстати. So it is more or less obvious that for the dodecahedron and also for the icosahedron, the Schläfli symbol will be, it will be, for one of them it will be 5, 3, and for the other one it will be 3, 5. Okay? In this case, we will draw 3 and 1. So,
То есть химазин тоже граф соответствует.
да, сейчас скажу. So, do you know what are dual polyhedra? Did I define it? Dual polyhedra.
I know the definition from Wikipedia. That is vertices and edges get exchanged.
In any dimension, you just maybe you can say that if you live in the dual space, all the linear functions which vanish on Fi, they will be the bound for the dual polygon. Or you can just for a vertex, you can draw a plane which is orthogonal to it. So the dual 2 cube is a co-cube. For usual cube, you will obtain octahedron. And for dodecahedron and icosahedron, they will be dual. So it is more or less clear from the definition, if we define alphas in this way, that if we pass to dual polygons, the group remains the same. So the group remains the same, and so it is the same for them both. You can,
Если граф такой растет.
ну да, в смысле, когда вы приходите к двойственному многограннику, у вас, ну, по сути, как бы ваша группа веер, которая действует на одном, она действует на втором. У вас отражения те же самые.
А куб будет правильным многогранником только в трехмерном
Не,
пространстве?
ну везде будет. Какой вы можете определить?
Он правильный?
Конечно, ну правильно. Вот. How can you define the co-cube?
А у него какой граф будет? Такой же, как у...
This one. Окей.
Символ Швеции это...
Да, давайте до октадра напишем тогда.
Почему символ Швеции это все тройки, а потом четверка?
Да. What is the Schläfte symbol for the octahedron? This is our octahedron.
3, 4.
Ну, короче, да, 3 and 4. So, if you write down the inequalities for the co-cube, you can define co-cube as the convex half of plus minus 1 at one place and zeros at all the other places. Okay? This is the set of vertices of the co-cube. And if you write down all the symmetries, they will be exactly the same as in the usual cube. Because if your map preserves M, then it will preserve the dual.
No, I don't get this construction. Can you?
Yes, this is the construction. I wrote down exactly the vertices of the co-cube. I state that co-cube in dimension n has 2n vertices. You choose one place where you have either 1 or minus 1, and all the other coordinates are settled with zeros. What about usual octahedron? You can write down vertices. This, this, and this. Okay? You have a square in the plane, and you have apex and the anti-apex. This is the set of vertices of the usual octahedron. Any other questions?
Правда, что двойственный к правильному, это правильно.
Ну, конечно. Сейчас.
Символ Швеции просто в обратном порядке записывается.
Ну, вы можете так обратно объяснить?
Нет.
Вот
Это
задача.
Это гипотеза.
Держите семинар, да.
Это в прошлом семинаре.
Ну, сейчас как это, да, никто не сделал. Да, это правда. Any other questions? Ну, мы сказали сейчас, если никто не решит, то кто решит. Если кто-то решит, то хорошо.
Чтобы решить, надо сначала ответ узнать.
Вы угадали. I'm sorry, it is still in Russian, but the definition is in fact the same as Wikipedia. And this is just to show that between these two faces, the number of faces of dimension k is 1 and of dimension k is big